Thanks a lot for this introduction. So it's a pleasure for us, Baorui and me, to give you a presentation about the Learnable wavelet transform. And so first, let's go for some motivation behind it. It's about acoustic monitoring. So what is it? Is that you have a machine that emits sound, and you want from the sound that it emits to know if it's in a good state, in a bad state, or to have some information about the machine. And why acoustic monitoring is particularly interesting? It's because audio sensors are cheap, easy to install, and maybe one of the most important, they are non-invasive. You just have to add them next to the machine, and you can record some information from it. However, this kind of signal, so acoustic signal, are kind of difficult to proceed, to use, to extract information from. So first, they are related to a high sampling rate. So it's signal with a lot of sample. And to use directly as an input of deep learning can be sometimes a bit difficult. Also, there is often a high noise level and artifacts. And the useful information can be difficult to extract. And finally, it can be sensitive to the different operating conditions. And usually what we do with this kind of signal is we try to find some representation on the Fourier domain or a time frequency domain to have more easy to process information. And here, what we try to do is to propose a deep model, so a deep learning model based on the signal processing methodology in order to extract some understandable and useful features directly from a sound signal. So first, I will present the signal processing background behind the method, which is a wavelet packet transform, and then the methodology, so the Learnable wavelet packet transform. Then two applications that will be presented. One, a basic one for anomaly detection, and then Baorui will present the slab track condition monitoring for classification. So let's go for the signal processing part. Here you have an example of audio signal. And for example, we can extract some feature from it, but here I present the energy, how the energy distribute over time. So it's just the square of the signal. So it has here a very nice time resolution, and that's all. And so the principal component of the wavelet packet transform is based on two simple elements, a low-pass filter and a high-pass filter. So the low pass here is represented in this, the frequency response of this low pass is represented here, and for the high pass here. And also there is subsampling operation. And so it will provide two outputs. And I can show the energy distribution over time of this output. And here then we have increased the frequency resolution by 2. We have the highest frequency and the lowest frequency information. However, due to a subsampling operation, we have divided the time resolution by 2. And so here it's a basic block of the wavelet packet transform, and the idea is to recurrently use this basic block. For example, again, a low-pass filter, a high-pass filter, a low-pass filter, and a high-pass filter. And this time, the frequency resolution is multiplied by 4. We have projected the signal into 4 band pass represented here. And however, the time resolution is divided by 4. So just a little remark that the subsampling operation is important, because if you don't put any subsampling operation, you do a low pass and then again a low pass and nothing happens particular. And here you do a low pass and then a high pass, and you remove all the information in the signal. So the subsampling operation is here to diffuse the frequency information to be able to, again, apply the low pass and the high pass. So, OK, and so we can continue like that. And then here we have 8, increase the frequency resolution by 8 and the time resolution by 8. And so we can add any number of levels that we want until we have something that looks like a spectrogram. So it's like an optimal spectrogram representation. What is particularly interesting also with the wavelet packet transform is like the Fourier transform. So you go from the time signal to a frequency signal, and you are able to use an inverse Fourier transform to come back to the original signal. Here it's the same, except we don't go to the frequency representation, but we go to the time frequency representation, and we are able to come back to the input signal by inverse wavelet packet transform. So it is possible only if the filters here have some properties, but I don't enter in details here. And one of the main applications of the wavelet packet transform is to perform some denoising. So why? Is because input signal, when it's structured, it should have a sparse time frequency representation. However, the noise in the signal does not have any structure, and it should be related to low amplitude coefficient. So what you will do is to add some hard threshold function that will remove the low amplitude coefficient, keep only the high amplitude coefficient that are sparse, and then when we perform the inverse wavelet packet transform, we can get a denoised signal. OK, so that was the introduction about the wavelet packet transform. And now I will show how we make it learnable. And so it's quite simple. It's exactly the same architecture, except the low pass, the high pass filter. So what are the low pass and high pass filter? It's just some coefficient. And we apply a convolution on this coefficient, and we make this coefficient learnable. We keep the downsampling operation, the upsampling operation of the inverse. And what we add is some activation function up here at the output of each filter and that perform the learnable denoising. So we don't use directly hard threshold function, but 2 sigmoid because it's easier to use in a network architecture. OK, and so the idea here is that maybe the signal has some specificities, and then we will learn the kernel of this filter to have a better representation of the signals that will maybe more sparse, and that we will be able to then it will be easier to remove the noise thanks to the learnable denoising. So the advantage of the architecture is threefold. First, it has a huge learning capabilities because it's based on a very simple architecture that can show a very nice representation of the signal. Also, it's very interesting because there is a natural way to initialize the learnable wavelet packet transform. We can initialize it so it starts exactly like a wavelet packet transform. And then based on the training data set and the loss function that we use, it will slide to something else. And finally, we have a clear interpretation of each parameter of the structure. So now it's just a small remark, because in the application, it will be this architecture that will be used or another one. So here is the architecture of the wavelet packet transform that projects the signal into a frequency band of the same width. But what we can do is only perform a cascade algorithm that only where the basic block is applied only on the output of the low-pass filters. And what is interesting here is that then we will have different outputs which will have different time frequency resolution. So the first output will have a bad frequency resolution on the high frequency, but a very good time resolution. And over the low frequency, we will have a better frequency resolution for the low frequencies. And it will imitate a bit what we use a lot for time signals, like, for example, a MEL spectrogram, where we focus more on the low frequency. So again, just to show what we do is the same. So we add we make it learnable, and we add the activation function. So first application, anomaly detection. So here is a data set that starts to be that contain 4 different machines, valve, pump, slide ray, fan. And what is interesting with this data set is that all the machines have a very different, all the sound of the machine have very different patterns. For example, valve and slide ray are non-stationary signal. However, pump and fan are stationary signal. So it imposes, when we want to apply a methodology in all the machine, to have a methodology that is quite general. And the idea is to perform anomaly detection. And the idea of anomaly detection is that the anomalies are rare and not necessarily representative of all the anomalies that can happen in the system. So we will make the learning on the LC signal only. And so here it's an example of what happened. So we learn the learnable wavelet packet transform to encourage parsimonious sparse LC sound representations. That to say, we use only the LC sound for the training, and we want a sparse representation. And here you have an example of a wavelet packet transform applied to a sound. And here it's a learnable wavelet packet transform, and we can see there is way less activated coefficient, so it's more sparse. And so when we get an abnormal sound, we get some specific features that can be related to the anomaly. And then so here is for the wavelet packet transform, and here for the learnable wavelet packet transform, the specific features are more are highlighted. And so it's easier to make the anomaly detection. Here it was a feature for the anomaly detection. So we take the mean and the max of each node, and also the mean and the max of the residual, because also it's interesting to see, we can see it, the system as an autoencoder. So we can consider also the difference in the residual for the anomaly detection. And then here we compare to similar method, and so for this case, the learnable wavelet packet transform has the best performance. OK, so now for the second application, I will give the talk to Baorui.
OK, hello, everyone. Gaetan has just introduced the learnable wavelet transform and its application in anomaly detection. Now let me introduce another application scenario, that is the snapshot condition monitoring based on acoustic signals. Here we propose an acceleration-guided acoustic signal denoising framework, which is a further development of the DESPON. In real applications, the acoustic signal radiated by the target object is often impacted by the environmental noise and other sounds radiated by irrelevant structures or mechanisms. In this case, the denoising performance of unsupervised machine learning methods like DESPON tends to be limited. Supervised methods usually require a training dataset composed of the pure signals and their noisy counterparts. However, in many cases, it is impossible to record the pure acoustic signals of the target object. Therefore, we propose to consider the measured acceleration signals, as their signal-to-noise ratio is much higher than that of the measured acoustic signals. So in this study, we developed an acoustic signal denoising framework that can learn a strong denoising transform under the guidance of the corresponding acceleration signals. And this is the architecture of acceleration-guided acoustic signal denoising framework. We also call it AGASDF. And the input signals to the AGASDF are different for the training and application stages. In the training stage, the AGASDF require both acoustic signals and the corresponding acceleration signals. The acceleration signal is passed through FDWT to be decomposed into wavelet coefficients, while the acoustic signal is fed into the death point to produce learnable features. The proposed loss is a trade-off between the reconstruction of the acoustic signals with the death point and the similarity between the wavelet features and the learnable features. So the loss terms we define here are the reconstruction loss and the guidance loss. Then in the application stage, I would emphasize that only the acoustic signals are used as the input to the trained HASDF to obtain learnable features, to obtain meaningful features. Therefore, this approach is very easy to deploy. And to evaluate the performance of the HASDF, we conducted a real-way field monitoring experiment in China. And since abnormal states of the snap tracks are rare in real applications, we use 3 types of snap track with different supporting conditions, the mortar, the rubber, and the spring support, to imitate the healthy and unhealthy states of the snap tracks. And the acceleration and the acoustic sensors are installed next to the 3 types of snap tracks to connect the acceleration and the acoustic signals as the train pass by with different speeds. And this table lists the test conditions of our experiment. We can see the train speeds are 20, 40, 60, and 80 kilometers per hour. And the train passes 6 times under each speed. And we also list the average duration of effective signals in this table. And based on the acoustic signals, we conducted a comparative study among different feature learning and extraction methods. We can see in the training stage, we input both acceleration signals and acoustic signals to the HASDF, but in the deployment stage, only the acoustic signals are required for each feature learning or extraction method. And we take the maximum and the mean values, mean coefficients of the time frequency or wavelet coefficients from each filtered frequency band of signals and features. And based on a multi-class support vector machine on these features, we can evaluate the classification performance of using different feature learning or extraction method. And then let's have a look at the results. As a preliminary study, the classification performance of using acceleration signals is evaluated, and the classification accuracy based on acceleration signals is 100% in all classification tasks. The classification tasks are shown in this table. We can see for the first classification task, the training dataset and the test dataset contain all train speed. But for the other classification tasks, we evaluate the classification ability when the train speed in the test dataset is different from those in the training dataset. And we can see in the table, the HASDF reaches a superior performance compared to other feature extraction and learning methods. And the second and the third classification tasks are the speed extrapolation regimes. The last 2 classification tasks are the speed interpolation regimes. We can see the speed interpolation regimes perform better than the speed extrapolation regimes in classification tasks. And there is another interesting result. There is a poor performance in training 40, 60, 80 kilometers per hour, and test 20 kilometers per hour. We can see the we can see it even hardly reaches 60% accuracy. It's because the signal-to-noise ratio of the acoustic signals with the speed 20 kilometers per hour is too low. So the target features covered by severe noise cannot be effectively extracted by the current feature learning or extraction method. Okay, that's my presentation on the snapshot condition monitoring, and let Gaetan report the conclusion.
Thanks, Baorui. Yeah, just to conclude, we propose a deep model based on signal processing that is able to have a good performance for anomaly detection, and also that lead to use acoustic sensor that when we can extract features that are similar from the ones that we can extract for acceleration sensor. As a perspective, we could propose some end-to-end deep model where we put the head directly on the deep neural network, and also analyze a bit better how interpretable are the features from the Learnable wavelet packet transform. Thanks a lot.
Thanks so much.